start recording. Good morning, ladies and gentlemen. Welcome to another exciting Robe talk. Today, we are so glad to have Alexei Savitski from Shell to present a topic on a poroelastic nature of multi-stranded hydraulic fracture in unconventional rocks. So this is a very good time to talk as well, because next week we're going to have hydraulic fracture in Texas side talk by Scott Reeves and Jordan from DTI. So before everything else, like we always do, we share a safety moment. That's the whole reason we're doing this series. We connect, entertain, and stimulate rock professionals during this pandemic when everybody practicing social distancing at home. The safety moment today is actually, I want to share, as you all know, Houston seeing, or Texas in general, are seeing another spikes in confirmed coronavirus cases. So people are talking about the Memorial Weekend parties, probably too much fun, or the young folks probably lack of sufficient protections when they go out. But either way, we are where we are. The key question is that what we can do differently to flatten the curve. That is one of the reasons why so many mayors in Texas draft a letter calling for governor to basically regulate, give them authority to enforce everybody wear face masks. I know it has been a long way to recognize this, but wearing face masks become one of the most effective ways to combat virus. So I want to share this with you. It's not from this, but from the mayors in Texas that everyone needs to wear face masks. That's for your own safety. It's also for people around you. Let's all keep that in mind. So today's talk, like I said, is very well timed. And Alexei, many of you actually know Alexei. I was joking, not joking. As a matter of fact, I know Alexei is a great technical guy. But I didn't realize low profile Alexei is so popular. Many of you ask for his prestations. And today he has kindly offered to release the recordings of this talk. So you don't need to do anything, just enjoy, sit back. And we're gonna release the recordings at the hydraulic fracturing community newsletter you have been receiving. So if you have not, then you send me an email. I add you to the email list. Alexei actually worked mostly in technology organizations at Shell. He actually graduated from France. He worked in France, but he graduated from University of Minnesota in civil engineering, got his PhD there. And he originally from Russia. So you speak at least 4 or 5 languages, Alexei, right? That's
I speak 5 different accents, yeah.
Wow, no kidding. You know,
but only 2 languages.
You are a smart guy. They say having a lot of fun from different countries. So with that, I think just turn the floor to Alexei. Again, for the rest of folks, if you have questions, please type in your chat window. Alexei will answer them during this QA session. We have this room up till 11 o'clock. Thanks, Andy Banger. Andy has been tremendously helpful to host this very popular series, as well as help release all the recordings. So I need to recognize his effort as well. So after that, Alexei, feel free to take over.
All right. Well, thank you very much for introduction, gang. And I'd like to thank you and Andy for inviting me to give this presentation and giving me time to do so. Robe Talk has been a phenomenal series of presentation. I'm really honored to follow in a series of very distinguished presenters and leading scientists or engineers in our field. This presentation and paper was prepared specifically for ARMA, which was cancelled unfortunately, although paper was accepted and will be published electronically through OnePetra. So if you're interested, you can download there. And the main objective I had in mind preparing was to steer a discussion around a very interesting set of data, which has been looked at in the industry, in petroleum industry, and some people in the rock mechanics community. And there have been several attempts trying to interpret the data and come up with models which would at least qualitatively describe what's going on there. I thought that the range of realizations or concepts that have been put on the table was good, but not wide enough. And my main objective is to widen it and open discussion and steer the community to look for a different family of solutions for this problem, which I think we all would benefit from at the end. So its ambitious title is on the poroelastic nature of multi-stranded hydraulic fractures in heterogeneous unconventional rocks. Let's start. So I don't assume that everyone is very familiar with unconventionals or is aware of stimulation and conventional rocks with hydraulic fracturing. So I'll start with a very, very simple cartoon. Oh, here. Think about petroleum setup where there is a horizontal well somewhere deep in the ground. We're looking at it from the map view. So it is a horizontal section of a well, and it is being stimulated. You probably all have heard that stimulation is done through injection of fluid and solids to create fractures and conductivity, which hopefully would be preserved and then contribute to production from the same well. So we first stimulate, then we produce from the same well. So what is not known is, so what we do know is what we pump in. We probably have a good idea where we do it, although sometimes there is uncertainty on the fluid isolation within the wellbore. What we don't know, what we haven't known for quite some time, is what happens away from the well. Oh, by the way, Andy, can you see my points, or I need to click something?
Yes, we can see that.
Okay, thank you. Thanks for confirming. And so we do know that it goes somewhere. So people have discussed different concepts, where fluid and solids may end up. There is a general and quite generic concept of stimulated rock volume, SRV, where enhanced permeability is expected, and there is a expectation, at least in some part of the industry, that the production is coming from this SRV, stimulated rock volume. So what you see on the map view is just a cartoon, two-dimensional cartoon, where we think that, well, probably there is something like a principal fracture, more like conventional hydraulic fracture. There is something unknown happening around it. There might be some complexity. We don't know what exactly. Let's just call it this hollow zone around fracture. And the question is, what actually is there? So it's a small scale. So several, companies and joint groups of companies led by GTI conducted very elaborated, integrated field pilots where they actually drill through these zones. And I'll mention on the next slide. So one published results from pilots were conducted by ConocoPhillips and Ingleford, and then there are published results from consortia led by GTI, Gas Technology Institute, which is private-public partnership. And they all observe something, so it's very thoroughly analyzed as a core through this fractured zone. And there are some very repeatable and systematic observations on that core, which triggered modeling work, and different interpretation concepts in the industry and in a technical community of rock mechanics. And that's what I would like to discuss. So I'd like to look at these results, quickly summarize what are the key observations that I'm interested in. I'll show some previous attempts of explaining this data. There are multiple ones. And then I'd like to throw in another concept, which illustrates how else the results of this stimulation could be explained. So the key observation I'd like to talk about, you can see here. So on the left-hand side, you see a photograph. It's from paper by Ratterman et al. Reporting on the ConocoPhillips pilot in Eagleford. At the top of this picture, you see a photograph of core and then CAT scan of the core and then FMI log. So FMI log and photographs are on different scale. So the core photograph is on, you can see full scale, shown on this black solid line, give you scale, and then this black line corresponding to FMI formation image log scan is 10 feet. So keep in mind this difference. What you see and what is consistent that there were interpreted hundreds of sub-parallel, apparently tensile fractures in the core. And that's not exactly what people expected in the beginning. So before first data of this type were released or acquired. So one uncertainty around SRV was about the role of natural fractures or natural fracture networks, DFN, discrete fracture networks, and percolations of fluid flow within this fracture system. And this fracture network might have the fracture sets in the network might have different azimuth and strike, and you would see some variations in the fractures that you would see stimulated in SRV. But this data show relatively consistent azimuth of those hundreds of tensile fractures created, and the number of those fractures is much greater than the number of perforating clusters which were stimulated. So if you were assuming single perf cluster, single fracture, that doesn't work here. So we get many more fractures and we have entry points from the wellbore. Also, the spacing of those tensile fractures observed in core and seen in ARMA or in FMI, quite denser than and smaller than spacing between initiation points in the stimulated well. So something else is going on there. And I'm neglecting here the details on re-stimulation of natural fractures. Some of them were re-stimulated. So in Eagleford actually there were very few natural fractures to start with. But on the right-hand side, you see a picture from already published results from HFTS1, which is Hydraulic Fracture Test Site 1 Consortium. So probably next, in the next talk, Jordan and someone else, I think. So, but Jordan is leads from GTI side presentations, and they will probably show more detail on this pilot, unless they're going to talk about HFTS2. And what you see here is again a photograph of a core at the top and then CAT scan at the bottom. And it shows a set of subparallel fractures. And what is also important that the orientation of the subparallel tensile fractures is roughly normal to the minimum in situ stress, and basically subparallel to the expected plane of classical planar single hydraulic fracture if you were to stimulate just one single fracture. So something happens in the right direction, but you have much greater density of events than you would expect. So how can you get this density of tensile fractures where you have dealing initially with almost intact rock in settings where you have very little natural fractures to start with, and then you can have case where you have quite more nature fractures to start with. Some of them reinitiate, some of them don't. But the observations are kind of similar in a very different geological settings. So the results that I'd like to focus on are presence of subparallel, large number, densely spaced, subparallel fractures oriented normal to the minimum in situ stress. So let's see how we could possibly explain it. So there have been a series of, this is all recent, so the data were released roughly in 17 and on and later, and there have been a few immediate attempts to generate complexity observed in core through different rock mechanics simulation work. I'll very quickly review them. It's not my objective to criticize them, although I'm happy to discuss that then. So what I do, I don't like about these different attempts. So first thinking was, well, maybe it's a GFN or natural fracture system which is present in subsurface, which drives this complexity that we observe in the core. And you can see paper from Srivastava, and it's a group of Professor Sharma at University of Texas. And they show results of simulations, a 2D snapshot of final configurations where there is a black line, solid line shows connected large hydraulic fracture, and then initiated natural fractures are shown in red. Again, so if you stimulate it from a well and then drill hypothetical synthetic core somewhere at offset distance, then you may observe quite some complexity. One thing, so again, it's not my purpose to go into details of all these solutions, but I'll just highlight a reason for looking for alternatives. Here, the reason would be that if you look at the intersections, so they suggest that much wider distribution of azimuth for intersected fractures or stimulated fractures would be a combination of shear and tensile fractures. And just by nature of this GFN model, you would expect quite some variation in the angles, which we don't observe in the core. Then there is a very nice summary paper by Bussetti, 2019, shows that different concepts, starting from on the left, single planar fracture. Clearly, we don't see it in core through data, and then there might be some stress interference effects where fracture starts to deviate again, but it doesn't create this great number of fractures, like hundreds of fractures per few hundreds of feet of core. Then there might be some complex rock mechanics effects, such as branching or multiple initiations from the wellbore. And they could possibly, they all suggest some spread in angles. So if you want to intersect them with an offset well, and you also need to be able to generate this whole family of branches to produce sufficient density. But that's the thinking in terms of, okay, what could happen so if you start one fracture, can it bifurcate and break down into new branches and create complexity, rather than relying on GFN, which is present in the subsurface. So it was very recent work, nice numerical piece work by, again, UT folks, led by Manchanda, 2020. It shows now brings it's out of 2D planes to the 3D effects, and you can see that branching or complexity may happen because of the difference in layers property in subsurface. So if you think about laminations or sedimentological layering, and layers can be at different stress azimuth or with different stress ratio or different mechanical properties, then in 3D, when fracture propagates and may start to stress interference may cause bifurcation and splintering at interfaces between different mechanical layers. If you look at this from the map view, if you project these fractures on a plane, it will create more complex pattern of intersections. Well, the problem is that the data that we have, that's not a projection. So I actually have one core taken through one particular depth, or if it was a slanted core, it was dipping slightly, but it was still, it's not a projection, but it's rather intersection of this solution with a line where core was taken, and right now, at least, this model doesn't seem to produce the level of complexity that we observe in the core. But but clearly, this is something that might well be happening in subsurface. Now, I'm getting close to how I would like to tackle this problem, and there is an absolutely phenomenal, in my view, paper by ConocoPhillips, Rotherman et al. 2019, where they move from looking at fracture geometries to analyzing subsurface pressure data and integrating them in a subsurface reservoir model. So it's a dynamic production model which calculates depletion, well, production of fluid from subsurface for these fractures and then depletion around the wellbore. And they had a very challenging task of matching offset downhole pressure gauges placed in an observation well. This is one of a kind in unconventional world so far. We may get more data in HFTS2, which is ongoing pilot, but this is only one which was published. And the successful attempt to represent production behavior with a model was to place a set of large set of parallel fractures with variable shape and size and geometry. So you can see this blue, green, red. They have some different characters and different conductivities, but the whole point is that they, in a production model, assume that they're dealing with a large number of parallel fractures, which is very consistent with observations in core and formation image log that I showed earlier. How you got a system of these parallel fractures stays beyond the scope of the paper. So their task was to match production, assuming that it's there. My objective in this talk is to review and discuss scenarios explaining how you could get this system there in the first place. So the ability to successfully match production give a little bit of support to this type of representation of effect of stimulation, hydraulic fracture stimulation in shales. Now, whether it's right or wrong, the question, so how could you possibly get there? So it was a very recent paper, very nice work by Fu and his co-workers from Lawrence Livermore National Lab. I think the focus was not so much on explaining how you could generate a set of parallel fractures, as you can see in this picture or cartoon, but rather they were focusing on if this is what's happening, so how could you upscale it in such a way that you could model propagation of this complex parallel group of fractures as a single fracture and represent the underlying physics in terms of loss of energy and mass balance. So it was, I think, a bit more about efficiency of representing this model in a hydraulic fracture simulation rather than explaining how you could possibly get this type of mechanical system propagating during injection of fluid. So there is an implicit, well, kind of implicit assumption in Conoco's paper that these fractures initiate from the wellbore. That's quite an important one, which means that every single fracture is connected to the wellbore, and then there is a high conductivity corridor just next to the wellbore. It's a near field, near wellbore phenomena, which is assumed. So there is not quite evidence. Well, there is some discussion about thermal data which might support it, but I would leave it as an assumption for now. And here it's similar thing. So we assume that we can, so there are multiple sources, whether it's a leak behind the casing, so cement maybe is not too good, or maybe there is a longitudinal fracture geometry zipping through the wellbore, and that's our source for multiple fracture propagation. But then once it happens, and if it's stable, then it can be efficiently modeled using the upscaling approach presented by Lawrence Livermore. That's what it is. Well, actually, all previous work was showing that it's impossible to propagate fractures simultaneously because stress shadowing would very quickly shut down most of the inner fractures. But that's beyond the scope of what I'd like to discuss here. So all these fractures that we looked at so far, they all assume that they were fed and created by injection of fluid from the surface into the wellbore and then into these fractures. So they're all connected. They're all filled with slurry, maybe with propellant, maybe without propellant, but they're all hydraulically induced and connected. Now, I remember it in one of the presentations, actually by Dmitry Garagash, that sparked when I saw this picture from quite famous paper by the Lanning colleagues from Stanford on mini dike outcrop. And I thought, that's look, what I had another analogy with what we saw in the core. The analogy would be damage or this choke shape damage of core when you bring low mobility core with low mobility fluid to the surface too quickly, like oil sands, for example. What happens then that you have too much gas in the system, and then you release stresses when you bring it to the surface, and that gas just break your core in a set of parallel extensional cracks, which is very unfortunate. And that was my analogy for where I had with core observation. But this is something different. So this is on a very large scale. So you can, so there is a minute dike here, and then I just highlight marked with red lines here, some, not all, dike parallel adjacent faults. So there are faults which were topic of many investigations. One of them is given in this paper by Delaney in '86. And in their approach, they didn't think that these fractures were created by fluid which created dike in the first place, which is magma. They interpreted that as a very plausible mechanism that these parallel joints were formed ahead of the dike, propagating dike tip, somewhere in this zone where my pointer is, or here in this circle. And they just formed in tensile field where they could tensile stress could just overcome the tensile strength of the rock whenever you have defects or heterogeneity. There is minor problem with this concept is that if they looked at whether the tensile strength ahead of the fracture tip would be greater than prevalent far field in situ minimum stress. But I think in reality, you need to look whether the actual failure criteria should include minimum stress, not far field minimum stress. So the local stress would be rotated, which means that I would expect these dikes to kind of fall off to the left as you go away from the tip, because the orientation of stress around the tip is changing. And these dikes seem too parallel to me to be consistent with this type of failure mechanism. But the beautiful thing is that in this model, and that's first time, we are looking at the set of subparallel fractures next to essentially a large hydraulic fracture, which are not connected to it. They're not created by fluid of this fractures, they're created by something else, by some stress alteration around the propagating fracture. And you can see from the kind of top view and some angle perspective, this dike zone and then a large set of subparallel fractures. Now imagine this picture I showed you on the second slide, where if you were to cross and drill through these fractures, you would see a set of high density and great number of subparallel joints. So this looks promising to me. Now, I need to move to a simpler solution I could think of to illustrate the concepts, and that's what I'd like to present in the next few slides. So the thinking is the following, that when we create hydraulic fracture, that hydraulic fracture itself becomes a source of high pressure, almost constant pressure boundary condition. So the pressure in the fracture during injection phase may change by maybe hundreds of PSI, maybe less. Variation of pressure can be few hundreds of PSI at most, relative to few thousand PSI of subsurface pore pressure and stress. So if you assume that in hydraulic fracture during injection time the pressure is constant, what happens in the direction normal to the plane to hydraulic fracture, which is shown on this cartoon? Well, your normal stress, which is parallel to the minimum in situ stress, will decline. And it will decline to far field in situ, well, sorry, blue one. So the far field in situ minimum stress. And pore pressure will decline too. They should be equal at fracture phase because of the equilibrium. And then they will decline, pore pressure will decline to lower value. because our pore pressure in the field is lower than minimum in situ stress. But their decline is governed by different features of the problem. The stress decline is strongly controlled by the geometry of the fracture, mostly its height. And pore pressure decline will be changing as pore pressure, as fluid is diffusing or leaking from the fracture, and there is a pore pressure diffusion in the normal direction from the fracture. So this pore pressure change will be changing with time. Stress will change too, but not nearly as much, so only due to poroelastic effects. And this pore pressure decline is not really sensitive to the fracture height as much as stress. The point here is that these two curves are controlled by different parameters, and at certain time and under certain condition, stress can become, well, pore pressure can become greater than stress and will effectively create condition with a tensile effective stress somewhere in the field. And this tensile effective stress can be sufficiently high to overcome some local strengths, tensile strengths, or defects, or plane for weakness, and generate fractures pretty much in the same way as hydrocarbon generation creates sets of extensional fractures in subsurface where pore pressure becomes greater than stress. Same happens when you have an uplift and pore pressure doesn't have a way to escape. And again, you get pore pressure greater than stress, and that creates pop-up tensile fractures. The key thing is that those fractures are not connected to the main one, and that's what is important. So I thought about what would be the simplest possible model formulation that would allow me to investigate this idea, and I couldn't come up with anything simpler or better. There's a plane strain fracture. You can also think about this as a very long fracture in out of plane direction, but we are just looking at its height. And then I assume that it's all low permeability, but there is some layer, very, very thin one, with high conductivity. Well, actually diffusivity, which matters here. So I assume that there is no flow anywhere except for this layer. It could be bedding plane, it could be very thin carrier bed or lithological unit. So that's where pore pressure diffusion happens. And in that case, I can look at this type of cartoon and plot my stress and pore pressure changes just at that level in this layer at coordinate y sub h. So everything here is elastic. Again, it's a plane strain case. So this allows me to get stress declining along this layer from maximum value right at the fracture to the minimum fracture, which is consistent with far field stress. So I solved this problem. It's a one-way poroelastic coupling. I do care about Skempton effect. So what you see here is a dimensional solution. Details are in the paper. For the purpose of addressing some questions, if you might have, I put all scalings on this paper, just so you can see how things are defined. So there is a dimensional time tool. Dimensional coordinates are scaled with a half height of the fracture. And then pressure is scaled with a far field. Pressure is scaled with difference between fracture pressure and far field pore pressure. So essentially, pore pressure is changing from 0 to 1, and stress is changing from dimensional sigma star to 1. So the first solution for pore pressure would be a Skempton effect. So as soon as we instantaneously create the fracture, there is a pore pressure response in this layer. And because right at the fracture, so the pressure is equal to the stress. So I'm looking at, essentially I put here boundary condition of 0 pressure. The Skempton effect will diminish with time. And then another solution is diffusion of pore pressure in normal direction from the fracture. That's my leak off in a thin conductive layer. And black solid line represents the superposition of two solutions. Dashed green line is my dying Skempton effect. And the red one is advancing pore pressure front. Then I can take simple 2D fracture solution and calculate stress around the fracture. There is no back coupling from advancing pore pressure front to stress. I think it's insignificant for the purpose of this discussion, but it definitely can be done. It will correct this solution, but wouldn't change its character. And then I'm just showing that picked some solution for some specific values of dimensionless parameters and show that initially, so there is a stress change along this layer, and there is a pore pressure propagating with time. You can see it going from blue, orange, green, red. Red is a late time case where pore pressure is already greater than stress. And this is exactly the zone I was expecting to illustrate with this solution, that yes, it's plausible that we can generate tensile effective stress zone at a distance from hydraulic fracture, and that is necessary condition for creating extensional fractures, which are totally isolated from the main frac. And then I looked, there are more details in the paper, but I looked at realistic set of parameters for unconventional play. I don't need to name any particular shale basin here, doesn't really matter. But you can get parameters in this range. I defined a set of dimensionals numbers corresponding to this range of actual physical parameters. And attempt was to see within this range of reasonable values of key properties, is it possible to generate phenomena that I'm trying to illustrate here? And I'm doing the next 2 slides, no, 3 slides. So what is shown here is solution just in one quadrant of the problem. So we are looking at top half of the fracture going from 0 to dimensionless 1. So this is the tip of the fracture. This is the center of the fracture. X is a coordinate going normal to the fracture plane. X equals 0 indicates the position of hydraulic fracture, or half of it. What is being plotted in just this zone is a solution for each horizontal layer. It's for each coordinate y sub h. I'm looking at what would be a solution if my diffusional layer was sitting at particular height of this fracture. And I'm doing the following. So I'm calculating solution for a given set of dimensionless parameters. I'm testing whether effective stress is positive or negative. And what you see here is a map of positive tensile stress zone. That's where tensile fractures are possible. They don't have to happen there, but they could. The streamlines here indicate the orientation of the maximum principal stress. So these fractures would be tangential to this streamline. So if something happens near the fracture tip, they would, you see, they would be dipping at an angle as you work away from the tip. That was my issue with solution by Delaney, where those parallel joints were created by tip zone just ahead of the propagating dike. Then I would expect some dipping as shown here to occur, which I don't think was present in outcrop picture. So as we increase in time, so we have more and more diffusion, then this zone is growing, right? So think about that we have this diffusive layer present at particular value of y sub h. And with time, so we get greater and greater diffusive zones. Again, it goes beyond the boundary of little screen where I choose to present my solution. And close to the center of the fracture, they're almost parallel to the main frac. If I go close to the tip, they're getting more dipping. If you go further away, there is dip too. And that's what I want to capture with this solution. Then I checked a couple of sensitivities, which I think could be quite important. First is sensitivity to stress anisotropy. Anisotropy here is between the vertical stress and the minimum in-situ stress. So how the dipping angle would change. I looked at 2 values from my permissible set of dimensionless parameters. Sigma yy is indicative of this, indicates this anisotropy. So the greater it is, the greater anisotropy is. And we can see that if it's more anisotropic, so sigma V minus sigma H mean is greater, then I get less of this dipping in my solution, but overall solution is not too sensitive. For example, the overall area and map of this tensile field is about the same, so I don't see any significant difference here. It's only in these streamlines that's we observe here. That's the only impact, which is kind of minor. So another thing which I was very interested in is, which is related to the huge problem in the industry, depletion or in an industry jargon, parent-child situation where infill wells seem to produce much worse. Yeah, I think I should be finishing in a few minutes, a couple of minutes. That depletion has significant impact on the fractures. My question was how depletion can impact the solution, and that's what I'm testing here. So the depletion would be corresponds to lower sigma star value, and it showed that if it had lower pore pressure when we are fracturing, then there is much less zone with tensile stress, which is generating the solution. Yes. So that's quite important. So the key factors which enhance creation conditions necessary for generation of these isolated tensile fractures are high net pressure and low difference between far field in situ stress and far field pore pressure. So if you deplete the field, it will really hinder creation of these tensile fractures. And that's what I would like to conclude. So the objective of this little study was to illustrate with the simplest solution that the concept of creation of totally isolated fractures roughly subparallel to the main hydraulic fracture is plausible. Yes, this may happen. The real picture may look quite more complicated when you put multiple hydraulic fractures and anisotropic system and multilayer. Oh, that's true. So you can get all kind of variation of more realistic solutions, but I don't think it changes the concept dramatically. Then what I haven't captured here is that these isolated extensional fractures can happen during pumping as high pressure diffuses through the rock or propagates, if you wish. But it also may happen during the leak-off. So when we stop pumping and we reduce pressure or we flow back fluids from the main frac, then high pressure would be still present, high pore pressure would still be in an adjacent rock. And if I drop my boundary condition pressure in the fracture too quickly, then I may create extensional stress conditions, well, tensile stress conditions next to my hydraulic fracture. I didn't study this, so it's intuitively quite clear how it might work. It would require a slightly different solution, maybe numerical, maybe the same convolution I use to calculate Skempton pore pressure response. I could use to change the boundary conditions, and it's another mechanism when it could happen. So it's not only during a couple of hours of injection, but then following the injection and reduction of pressure in the main frac can create conditions favorable for creation of isolated extension fractures. Then it's quite important in this model that the formation is roughly low permeability. So you may see if you start to play with it that the diffusivity needs to be in a certain range when it's not too high. So if you're in conventional rocks with very high, like sandstone formation with very high permeability, you wouldn't have extension of this pressure diffusion flow, and you wouldn't get this tensile zone anywhere away from the main frac. Similarly, if you have very low perm formation, like in tens of nanodarts and nothing else, then pore pressure would take forever to diffuse through the system and you wouldn't get it. So you need to be somewhere in between that can be further investigated. So here I was thinking about maybe microdice scale of permeability over a very thin zone. But this range of diffusivity is another important feature of the concept. And what I haven't studied here, but this would be completely consistent with observed microseismic response, which happens far away from hydraulic fracturing very quickly and very sensitive to the depletion, by the way. because the same high perm laterally continuous layer or bedding plane, which transmits pressure here to create tensile fractures, can also be conduit for high pressure to trigger microseismicity. Imagine that you have an atrial fracture at appropriate stress state, intersecting this high diffusivity layer, and then we have this high pressure diffusion front going. It can go very quickly if diffusivity is high, which is likely. So you have very low storage coefficient there. And microseismic can be very related, in unconventionals, can be very related in terms of mechanisms for creation of these isolated fractures. Something I'd like to bring to the attention of community, but I haven't studied quantitatively. So very important observation from this simple solution is that depletion would significantly eliminate possibility of creation of these isolated fractures, because it creates greater difference between in situ stress and pore pressure around hydraulic fracturing location. That's important. So that would be consistent with detrimental impact of depletion on quality of hydraulic fracturing in infill wells. And obviously, so all kind of complexity related to stress interference, multiple fracture propagation, layering can be accounted for numerically if needed. I would greatly encourage community, especially academic community, to look into it. It's important, and last point here before we finish, is that it matters which concept is right or wrong, or which one represents what happens in the subsurface. Because if our complex fracture system is fully connected to the wellbore, and all of these fractures can be conduits for hydrocarbon to get from subsurface to the wellbore, that would result in one type of reservoir models to capture production behavior. If these fractures are fully isolated, may or may not be important because they enhance permeability, but they're not connected to the main hydraulic fracture system, their impact in a production system will be different, and they need to be captured differently in the reservoir simulations. So understanding which mechanism is actually at play here is critical to making right realizations in reservoir simulations. So that's what I want to present. Again, my real objective is to steer discussion and bring attention of community to different types of explanations for fantastic results that were published by ConocoPhillips and then GTI. And I'm happy to answer any questions you might have.
Thanks, Alex. Feel free to look up the chat window. I see a lot of questions in the chat window already. Feel free to take on them.
Okay, I'll go in a chronological order. So the question from Yegor. Yes, stress decay is comparable to frac height. Well, I'm not sure why it's not what was observed in the field. What was observed is that everywhere we cored, we saw fractures. So you can think about spacing. So fractures don't need to be necessarily away by hundreds of feet from the main frac. That really depends on set of parameters and complexity. I don't think this simpler solution I presented necessarily captures the right stress state in fractures when you have multiple fractures spaced at roughly 30 feet or 10 meters from each other. So that needs to be accounted for. I'm just saying that in between fractures, just because we have fluid pressure greater than stress in situ, we have variable pore pressure and stress field. And there are some spots where stress is greater than pore pressure, and that would be sufficient to create, or necessary to initiate these fractures. Very good question. So what would be the exclusion zone around the fracture? How close they should be? This really depends on the details of the model and assumptions. So in this model, indeed, so if I go back, sorry, how do I do this? Yes, if I go back, depending where you are, so you can be like here, half fracture height away, so there is nothing you expect to happen. I'm looking at this dimensionals time 10 and the lower left set of snapshots. And indeed, there is an exclusion zone that's where you wouldn't see any extensional fractures. Depending where you are, you have different geometry of this map. But again, so if you start to put the heterogeneous layering and stress interference from multiple fractures, which are there at the same time, I may get different map, and I cannot answer the question. So whether exclusion zone would be very large or very small, depending where you are. That's something that needs to be investigated more carefully with more adequate numerical models. That's to answer Yegor's question. Well, that's okay. Questions from Yangqing Lu. This time, I need to go back and recalculate these times. It could be quite large, but actually dimensional time also depends on diffusivity. So if you go and look here, so I was assuming time in this models from 1 to 2 hours, but diffusivity have very wide range of uncertainty, and I don't quite know what it is. So if it's high diffusivity, and so timing is still 1 to 2, but if diffusivity is high enough, so I can get to these dimensional times. So all of them are within this range of physical parameters. So no, we're not talking about months of injection time. We're talking about hypothetical high diffusivity thin layer instead. A question from Eddie Sibritz. Well, I'm not sure about density. That's a very good question. So I think I would refer probably to PhD thesis by Tashubai on extensional fractures constrained by thickness of lithological units to these bedding planes. As a rule of thumb, what I learned from that work is that spacing between fractures is similar to the height of the lithological unit. So their height is roughly one-on-one with spacing between them, because this relates to another question. So when all we know from the core data is the spacing between fractures, but the question is, what is the height of them? We don't have data. So I was hoping that maybe the spacing tells us something about the dimensions beyond the core. And clearly, a particular location of fractures in this model would be driven by local heterogeneity and weakness in diffusive bedding plane or thin lithological units. Well, I'm happy to discuss it offline, so if there are more questions, I do. I'm looking at next question, so by Bo Lu. Water hammer, that's a good question. Well, I'm not sure whether water hammer can extend that far away. So typically this core. So the question is whether water hammer effects needs to be considered here. Well, I'm not sure how it's applicable to poorly consolidated sandstone. As I said, the key assumption here is that diffusivity for this to work needs to be in a relatively special mid-range, not too high and not too low. So in unconsolidated sandstone, diffusivity is on a very high end of the spectrum, so this wouldn't work. Whereas a water hammer itself could be, which is observed in unconventionals, could be related to creation of these fractures. I don't think so, because it would dissipate very quickly as you work away from the wellbore, and fractures are observed at quite some distance. I think that the flow back and the release of pressure from the fractures can be more important parameters. So we first create these fractures and then they close. And as they close, now imagine that you have a distribution of permeabilities or diffusivities in a vertical dimension with multiple laminations and layers. And then Some of them take longer time to pressurize, but they will take longer time to depressurize. So when loading of the fracture, when we propagate, it happens too quickly for most layers to react, but also unloading, so when we close fracture, release pressure happens too quickly for lower diffusivity layers. And in those layers, this trap pressure might exceed local total stress and create tensile stress conditions. That would be very interesting mechanisms to look at. Mahdi, Haddad, slide 7. Okay, I didn't number slides, unfortunately. And effective stress is controlled by BO coefficients. Well, what I do here now, the stress here is a total stress controlled by, no, for failure criteria, I'm not using alpha, BO alpha. So effective stress, BO effective stress is applicable to elastic calculations. So it is related to the strain, elastic strain, and I'm looking at failure criteria where pole pressure exceeds total stress, assuming that there is zero tensile strength. Well, if there is some finite tensile strength, it needs to be overcome as well. But I assume that considering the large volume of very heterogeneous rocks, there would be some spots with very locally very low strengths, and that's where these fractures could pop up. So the stress I'm calculating here is purely elastic calculations based on pressure in the fracture and fracture geometry. And geometry here is the simplest possible 2D fracture, Snedden fracture. And there is no pressure gradient within the fracture, so that's neglected. Ahmad refers me papers. Well, if it's Ahmad I'm thinking about, then I've seen a couple of other papers which I didn't put here on multiple fractures. Those were less related to what I wanted to show, but thanks for reference. I'll double check on these references. Thank you. Another quote.
Alexei,
yes.
Sorry to interrupt. Those questions actually are very nice. I think Andy can output all the questions in the email and then send to you. Might follow up afterwards.
Okay. Are we wrapping up? Gang? Do I need to wrap up now or do I need to continue? I can hear you, gang. Yeah.
Sorry, Alexei, I was replying in the window. You can take your time. You can stay if you'd like, and I'm happy to output the questions to you as well. But if you'd like to stick around, that's no problem too.
Absolutely, yeah. I can stay for another 10-15 minutes if people would like those questions. So question, but again by Bo Lu.
Oh, sorry, Alexei, my internet cut off. But just want to see the last thing. Next week, as I mentioned, next week we're gonna have Scott Reeves and Jordan Zierzobeck from Gas Technology Institute and present the hydraulic fracturing test sites, a successful public-private partnership to advance the science of hydraulic fracturing in the Permian Basin and beyond. Stay tuned for the meeting invite. Will be announced at hydraulic fracturing community newsletter this weekend, along with Alexei's recording releases. Yeah, Alexei, feel free to address the rest of questions. But for the folks that have to leave, yeah, stay well and healthy. We're going to see you next week. There are more fun to come. Thank you, Alexei, as well, for sticking around. All right. Go ahead.
As I said, I can stay for another 15 minutes. And my apologies to Scott. I forgot that he was giving presentation next time. Below, so what's a key component to deal with simulation of diverter agent effect on heterofracture propagation? The new Welber diverter and far field. Well, I'm not sure it's I can address it within the scope of this presentation. I don't see immediate connection, so maybe we can discuss offline. Sorry, for Erfan. Can you comment on how far propane was transported into the stranded daughter joints? Well, I don't think it was. That's the whole thing. So the question is, the observations from published results of GTI consortium and HFTS1, and hopefully in the future of HFTS2, and also results published by ConocoPhillips, I don't think they show that the stranded fractures were propped. So there are some traces of smaller size 100 mesh propane found in more joints than you would think, but it's difficult to tell whether there were plays there in the process of hydraulic fracturing or there were mix up in the process of coring and retrieving. And so it's quite possible that, so if they're stranded, then no propane is supposed to be there. Actually, no fluid needs to, hydraulic fracturing fluid needs to enter these joints. So it may or may not have time to diffuse through conductive flow into these joints. So it can be just popped up by formation, water and oil, which are there. And that makes a difference in how you would implement this fractured system in reservoir simulations. Another question from Diego. That concept of fracture generation after shutting sounds plausible in view of small fracture spacing observed in the field. The stress will be reduced on a larger scale, but the pressure will decrease only within the diffusion zone. Then the pore pressure diffusion zone will be then govern the spacing, and it can be on the order of a few inches. Absolutely. So that's what I was trying to indicate with in a summary slides that I just looked at the injection part because I thought I was looking at the simplest possible problem to illustrate the concept of creating pockets of tensile stress in the subsurface due to hydraulic fracturing, and just highlighting how more complicated it can be if you bring heterogeneity or multiple fractures or include for multiple injections and flow back and pressure decline. So the thing is, which is more complicated, is how do you release pressure from the fracture? And the actual flow back happens much later. So when flow back happens, you already probably diffuse most of the fluid in the subsurface. So I think a more delicate model would include cross flow of fracturing fluid between higher and lower diffusivity layers. So imagine that you are in a very distributed system of permeability or conductivity. It may be like bedding planes, which I know Van Goten labs have been investigating, or it can be more siltier zones versus more shaly zones and more controlled by sedimentology. But if you have a significant distribution of flow properties like diffusivity, then when you stop fracturing and you isolate the zone, the pressure will decrease and fluid will diffuse in a higher perm zones, but the low diffusivity zones by that time will be pressurized. So in this cross-flow situation, it is lower diffusivity layers which experience high effective stress or tensile effective stress conditions. This type of modeling would probably need to be done numerically. I haven't looked at this, but that's intuitively what I would expect to happen. And indeed, so when we drop pressure at the boundary, then failure can happen much closer to the fracture as compared to when we inject fluid. Good comments. Xiaowei Wang, assuming the subparallel tensile crack does initiate locally in a thin layer interface, how can it sustain subsequent propagation of the frag growth to a larger fracture? The fluid has to keep flow through permeable thin layer, which cannot sustain large rate unless the core happens to hit the hypom layer, which is to consider. Well, I think that there is no. So my thinking is, and that was a big challenge, so conceptual challenge I had to face. The data are coming not just from horizontal core, which is narrowly located in a particular zone, but some data are coming from slanted core, which is crossing multiple bedding planes. But the frequency and density of these fractures, while variable, is quite high. So the question is that if the mechanism is reliant on diffusive layers, then this diffusive layers needs to be frequent. That's the conclusion I take by trying to reconcile frequency of layers and the directional survey of this core, which is crossing bedding planes. Maybe it happens on bedding planes, something which has been already discussed in the industry. Maybe the cyclicity of the siltier zones at a small scale is much greater than we would imagine. So overall net to gross is very small, but the frequency of this percolating path, which is laterally continuous, can be quite greater. That's possible too. And you don't need to pump fluid there. This is a side effect of hydrorefraction. It happens beyond the tip, so it's not at the tip side. It may happen. It may be enhanced by tip. Maybe initial damage is done in tip by mechanism described in Delaney in colleagues' paper. And then by the time hydraulic fracture passes that zone and then diffusion takes place, there is already some damage which enhances creation of this pop-up stranded isolated tensile fractures. That's possible too. And I do expect that in this scenario, these fractures will have very low conductivity, and the main role would be to create more vertical connectivity, because they clearly have some vertical extent, although we don't know how significant. So they change permeability architecture in the reservoir, but they're not truly stimulated and they don't have prop conductivity in this scenario, of course. That's why it's important to clearly define different scenarios and try to eliminate wrong ones and try to narrow them down with additional data. Another question by Ahmad. Does the solution consider crack or half plane? Well, it's a full plane solution, but I'm showing, because of the symmetry, I'm just showing top half of the fracture and adjacent rock in a quadrant, well, rectangular, which is limited by the half of the height of the fracture. I'm not showing any solution beyond the tip of the fracture because there is no fluid diffusion there. But there's clearly stress changes there. When we look at 3D cracks in poroelastic rock, we don't see pore pressure exceeding the stress. I would challenge this. I think that we don't see pressure exceeding stress. It depends. What I was trying to show here, that I do know that if I put in any realistic 3D heterogeneous, you name it, fracture, if I place it in information, then pressure and stress and normal stress at the fracture plane must be the same because of equilibrium. I know this. I know that far away in a normal direction to the fracture plane, my stress is greater than pore pressure. I know that both decay and they approach different values. They start from the same values, they approach different values. It's what I was, sorry, let me get back here. It was I was trying to show on this cartoon which started all this exercise. I know boundary condition and I know far field conditions. I do know that the transition between boundary condition and far field is governed by different features of the problem. They are not totally correlated, which means I can select such set of parameters, and that includes fracture geometry or configuration of multiple fractures and diffusivity, of pore pressure. So I can select such properties that I will generate tensile stress. So I wouldn't probably agree with a more strict statement that in 3D pore pressure doesn't exceed stress. I'm fairly confident that you can generate this type of solution in 3D by selecting suitable parameters. All right. Go to the next question. I didn't finish it, sorry. Even if it does it at a small t, then that only satisfying crack initiation criteria, not propagation. Absolutely. So I don't say that there is a propagation. Actually, I don't know what happens with these features at all. All we know that at the end of the stimulation, and quite late actually, at the end of the full well stimulation, and when pressure was dropped, so we don't know when things happened, and we don't know the evolution of things. We only know that when we drill through this zone, we cross multiple parallel fractures. And I wish I knew the extent. They may be as long as the main frac if that diffusivity that I'm postulating here is continuous. I have no idea about their height. That's a really big question, because if it's significant, then it means that we start with unconventional place where, for one, we know that they're not in equilibrium. If you look at the local pore pressure and unconventionals in shales, the local pressure gradient is way too high. So that it means that they're not in a vertical equilibrium. But as soon as you play fractures there, and if you create hundreds of these, significant number of these tensile fractures, they provide vertical connectivity. So you immediately are able to equilibrate pressure within the system, and you enhance production between different layers, low, high perm. So I would love to know the height and extent, and it goes back to Eddie's questions about spacing, that maybe spacing is a key to start to look at how tall these fractures could be. But I don't think we have data to answer this question. And I don't think they're propagated. They pop up. It's almost the same as when you retrieve a core with low mobility, like bitumen, to the surface too quickly. You bring it up, you unload from the core barrel, and it pops up. You get these cracks all over the place. That's what I was thinking of. Maybe it's related to the mechanism observed in this dike parallel, adjacent joint sets parallel to the dike. Maybe. It looks very similar. I'm going to the next question. Deepen Gala. Whether these fracs would enhance leak-off or pressure diffusion from main frac, I don't think they're significant for the leak-off, to be honest. I think they might change the character, for example, if you run defeat, but defeat is happening at smaller time scale. So I don't really know whether they're important. The closure of the fracture, at least large fracture, can be impacted because these fractures clearly create some storage. But I don't see them enhancing leak-off itself. All right, Anthony. Thank you, Anthony. Chen-Ho. Excellent question. So I don't think, I haven't come across any chemical tracing that would allow us to see where frac fluid in these joints. I don't think it was done. So I think most of the diagnostics was related to analysis of different propant and tag propants. I think it would be really great to somehow trace fluid and see whether you can get frac fluid in these stranded fractures. That would be very enlightening. It could, for example, it could indicate, well, oh, there is one actually interesting set of data presented by Konica Phillips in the series of papers on their pilot. They look, which is not related to fluid, but it also helps us to analyze the situation. They they observe that these tensile fractures occur in swamps. So there is a bit of change in spacing or frequency if you look at all fractures along the wellbore. And they observed that if you analyze, do the spectral analysis on the spacing, that the swarms of fractures, if I'm not mistaken, it was like 4 out of 7 stages in the paper indicated the spacing between swarms of fractures to be very close to the spacing between perf clusters. So if I'm not mistaken, it was something like 45 feet perf cluster spacing, and then the swarms of fractures were spaced at about 47 feet. That was very interesting, and so I recommend everyone interested just to go and look at all papers published by ConocoPhillips and Rotem on their pilot. But no, I haven't seen any evidence of frac fluid in these fractures, and I think it's something that could be done, or maybe we just haven't seen all results. Next question, I'm not sure who that is. What evidence exists that fractures observed in core samples from your first example are not due to core recovery? That's a very fair challenge, and there are a few people very carefully analyzing, like Julia Gale, for example, very carefully analyzing these fractures in core. I think on that first picture I also showed, let me show it. What you see, this is a high quality formation image log from Eagleford pilot. So it shows not exact, no, it's not one-to-one correspondence, but it shows closed space fractures of same nature, and some of them can be mapped with fractures observed, and the core is discussed in the paper. So there is evidence that this is something that really happens, whether each fracture was observed and core was created in the subsurface, so that needs to be looked at one-by-one cases. But there is no doubt that good number of these fractures actually happen in subsurface. Wei, your question. Thank you. Propan analysis from HFTS, I assume 1, shows that most fractures have at least some propan, although to what extent that propan was introduced during drilling is unknown. Have you observed evidence of propan distribution that supports the mechanism? Well, but I think you answered these questions. There is no conclusive evidence that propan was placed in fractures in subsurface. I think in ConocoPhillips paper, or one of their papers, they very thoroughly analyzed it, and they were referring to definitely prop fractures in subsurface in cases where there was an indentation due to propan particles, which happen at high stresses in subsurface. So where they saw this damage or indentation of propans into formation, that was an evidence that it did happen in subsurface. But there are a few papers specifically addressing propan placement and analysis of propan placement for these pilots. I recommend to look at that. But no, we don't. Some smaller propan particles could be mixed up in the process of drilling and coring. You're absolutely right. Another question. So in the example of the subparallel fractures near dike, this is a region where compressible fluid in dike cause changes and drop in the stress, minimum stress and unloading of dike walls. How is this similar to your hydrofracking model? Well, I think you exactly explained the analogy I was trying to make. So you have a hydraulically induced, well, in this case, magma-induced fracture, which propagates there. It's driven by fluid. That fluid may diffuse and pressurize the fluid in an adjacent rock formation. If there is a suitable diffusivity, then this high pore pressure can propagate, and based on all other conditions can create this tensile stress. With dike, situation is a bit more complicated because you have strong thermal effects at the same time, and which we can almost neglect, I think, in hydraulic fracturing here, because far away from the wellbore, frac fluid heats up very quickly to the formation temperature. With dike, it's different story. So clearly there is a thermal effect that needs to be considered. Chenko, if the entire hydraulic fracturing process were modeled as a true dynamic stress wave propagation, okay, would the pore pressure away from the main frac increased? Like in undrained conditions, would the dynamic process be faster than the diffusivity process? That's a good question, because I think with dynamic, well, I think with dynamic process, it's almost like putting yourself with your hair. With dynamic process, I don't think pore pressure can exceed the stress, because your stress. So the wave, I think, would affect effective stress, which would be split between pore pressure and total stress. So actually, I have had time to imagine this with propagating wave, you can get pore pressure exceeding total stress because of the wave. I think this wave lifts all the boats. I might be wrong, but just intuitively. I didn't look at this in more detail and calculations, but that's what I always thought about the wave propagation poroelastic medium. Okay, another question from Yegor. The model is based on leak off and pore pressure change. Yes. In the context of magma dikes, there is no leak off, but fracture strands are still observed in the field. Any comments? Why do you think there is no leak off? That's a good question. So I'm not sure there is no. It depends what you call leak off. I think there is a high pressure boundary condition there, and I don't say that this trivial mathematical description that I presented can explain dike parallel joint sets problem. I just drew analogy between observations and hydraulic fracturing, core 3 shown on this slide, and schematics of those dike parallel joints. I thought that they're remarkably similar in my view. So I was thinking about mechanisms in which these fractures could be completely isolated from the main feature. That's what it is. I'm not specialist in dikes, but I would be surprised if there is no pore pressure change due to high pressure of the magma in the hydraulic fracture. But that really depends on what happens with thermal effects and thermochemical changes at the fracture boundary. Do you expect some seal there? I'm not sure. We need to ask geologists. But good question. So if this could explain something as fundamental as this dike parallel joints, I would be very happy if someone would do this. Thanks to everyone who enjoys the presentation. I really enjoyed the opportunity to present it. Fish and Liu, in the core experiments, is it possible to maintain and measure the saturation change of water on the fracture? Just to confirm the hypothesis. Nice talk, thank you. Well, I challenged Andy actually last year about this. So Andy, maybe you would be the best person to answer this question. I think it's quite difficult because you need to create pressure in a sample which is greater than confining stress. So you probably cannot do it from outside because you would have issue with seals. And if you do it from inside, you can just frac your sample. Andy, do you have any comments?
Yeah, I mean, I guess the issue is in a traditional triaxial cell, you know, if you're trying to core flood, if you have pore pressure higher than confinement, it sort of channels along the inside of the membrane. But yeah, I think there's some other loading paths that one could consider, but maybe that would be a more detailed discussion offline.
Yeah, I think if anyone wants to try to do this wonderful experiments, my guess that success is likely if you first saturate, pressurize, and load sample, and then play with unloading. So rather than literally mimicking this injection process, you try to mimic unloading part of it, where confining stress is dropped when sample is already pressurized. It's more like core damage experiments. But then the question is how to generate the gradient within the sample to study the spacing between these fractures. Challenge on from Peter Wang, leak off in only one layer. This may not be a good assumption. Well, it's a good assumption to illustrate viability of the concept. It's not a good assumption to simulate a realistic fracture, but in that case, I would also challenge presence of single fraction, homogeneous isotropic rock, right? So you would add all these details. And as I said in discussion with Yegor, that in reality, you would probably put a distribution of permeability or diffusivity in multiple layers, and the distribution would be wide enough that some layer would look like the only layer where leak-off happens. So you can always put the layers with 20 nanodarcy, which some people believe is intact shell permeability, and some layer with 10 microdarcy, and this 10 microdarcy will look like the only layer I showed in this solution. It's an idealization, it's a fair challenge, but I don't think it would change conclusion. Okay, let me answer a couple of more questions and then we'll probably need to wrap up. Another question about dikes, that subparallel fractures and dikes mean that stress around the principal fracture is modified, including the minimum stress, so that you cannot assume that the fluid pressure is constant in the minimum, or the minimum pressure doesn't change with time. Minimum pressure, I'm not sure what it means. The point here is that during propagation, the frac pressure is very stable. That's what we know. So there is net pressure variations, but they're in the order of lower number of hundreds of PSI at most. Then we know that far field stress pole pressure are fixed. We know that stress and pole pressure around the fracture are changed. So in this solution, I'm just trying to capture one particular simple solution for this changing both stress and pressure and saying that they change due to different factors and controlled by different parameters. And I can play with these parameters to generate solution with a tensile effect stress zone. That's what it is. So, right, and last question from Yegor. We'll stop here. Agree on thermal effects being crucial for dikes? Yes, most likely. Agree with you. And also on pore pressure increase due to heating. This is a good point, but that would be part of the thermal effect. So I also suspect that in dike propagations, there might be a component due to fluid diffusion. As soon as you generate high pressure at the dike boundary, then there is a diffusion happening in the formation itself through connected pore space and through mobile fluid in the formation. That was the point I was trying to make. I can only humbly imagine that given the viscosity of magma and its ability to solidify, which will be significantly enhanced in the pores. Well, I don't think magma flows. You don't need mass transfer to generate this diffusion. Even in this solution, so I didn't bother to do it. I leave it for people with more skills and more time in academia maybe to do it. But the invasion zone by frac fluid can be quite small, but the pore pressure propagation can be quite far. And that's what I suspect happens with microseismicity, because you need a very significant pore pressure change to generate tensile fractures, but you may need maybe just few % change in the pore pressure to trigger microseismic event if you have a nature fracture intersecting one of these layers with high diffusivity. And as you know, it's a parabolic equation, so your pore pressure is changed instantaneously everywhere. So this 5%, few % pore pressure change front will extend way beyond the dimensions of the model I showed you. And that if your diffusivity is right, then you can get a very quick microseismic response at significant distance from injection points using exactly the same mechanism and same conduit. All right, I believe I answered all questions. Thanks to all of you who stayed longer to ask questions, and I really appreciate your participation. My main objective is to bring community's attentions to different explanation, potential explanation for amazing results which are getting published now in the last few years, but now as well from this complicated integrated pilots with core material obtained through stimulated zone. I hope it will trigger more work and will produce more realistic models which account for multiple fractures, more realistic perm distributions and heterogeneity in the system. So that's my objective. Or challenges to the concept. So I would be very happy if we could narrow down the number of realizations to a smaller set. That's all I wanted to present, and thanks again for the opportunity to do so.